The seamless functioning of the grid is important for any network operator, electricity provider, or industrial company in today's increasingly distributed energy landscape. Automation is revolutionizing these processes, and for more perspective on this, I'm pleased to bring in Ronald Kubelec, who is the CEO of Electrification and Automation for Siemens France. Ronald, thank you for joining us. Can you define the role of automation in the landscape of the energy transition, and why is it important?
Thank you first for the invitation. The automation is one of the key of a successful energy transition for many different reasons. First, we need a very robust infrastructure. It's about transmission grid, it's about distribution grid, and these grids are affected by electrical faults. You cannot completely avoid it. In this case, you have to react. And of course, the robustness of the grid is important to be able to transmit, to distribute the power. And currently, with the increase of the renewables, we face additional challenges. In the past, we were more in a unidirectional power flow from big power plants, nuclear power plants or gas turbine, towards the customers. Nowadays, we are in more multidirectional because of the integration of renewable at every stage, at every level of the grid, starting with low voltage grid with prosumers, but also with implementation of wind farms or photovoltaic power plant connected to the distribution grid, and of course also with offshore wind farms and other kind of renewable connected to the transmission. And these multi-directional topics create new challenges, for example, to detect the fault, to react properly, to open the circuit breaker in case of faults, but selectively, not to trip a too large amount of customers or facilities. And there are also some other electrotechnical effects. Big power plants feeds a lot of a big level of short circuit current that's quite easy to detect. Renewables do not have the same short circuit power generation in case of electrical faults. That means that you need more sensitive functionalities to detect this kind of faults. But parallel to this, you need also to be stable, sensitive, but very stable. And for this, you need intelligence processing capacities that are able to operate with a very fine-tuned algorithm. This is one of the topics. Another topic is about the regulation. The electricity grid needs a good balance between power generation and consumption. And if there is an unbalancing situation, then you have an issue over voltage or under voltage, over frequency, under frequency. That's an issue for the stability of the network. And this is in the responsibility, for example, in France, of the transmission grid operator to guarantee this balancing, this stability. But for this, it needs also some solution. A part of the solution are decentralized in the electrical substation, for example, for the regulation of voltage. A part of the solution is in the central dispatching, with again some automated functionalities, but also with human operation. And all of this creates an increase in the needs of processing many different information because of the various situation in terms of power generation, because also the consumption is not in each case in the same region, or the big consumption is not in the same region as the big power generation. And for all of this, you need, of course, to extend the grid, but you need also more intelligence to be able to deal with this much more complex situation. And that's valid for to protect the grid, the infrastructure. That's valid for the monitoring. That's valid for the regulation And also for intelligent functionalities like switching of power sources in case of events, electrical fault or climatic events, these kind of things.
Ronald, you mentioned that Siemens' role is more complex with the increasing penetration of renewables, and this also requires smarter algorithms. You all are having to predict certain situations for customers in order to optimize their efficiency. Can you provide some practical examples of this, please?
Yes, there are many examples. I will just give two quite basic examples. The first is about the temperature monitoring the switchgear. One of the most usual problem in the switchgear is a connection between the cable and the switchgear itself. If this connection is not done properly, then you have a temperature increase, and it can even be worse step by step with a fire and a big damage in the substation. And through a quite simple monitoring of the temperature in this cable connection, you have already some signs that something's going wrong due to this connection. And you can, for example, put a very simple temperature monitoring with some thresholds and these kind of things. Monitor it permanently and sending an alarm to the maintenance team, for example, or to the operator if the temperature is going too high. Of course, this algorithm is much more intelligent and take into account the current flowing and the ambient temperature, this kind of things. But it gives an alarm called for action if temperature is going into the risky zone, let's say. This is the first example. The second one is a monitoring of the reaction time of the circuit breaker. Circuit breakers are in our world very important to trip to open in case of short circuit, of electrical fault. And this circuit breaker have to be able to open quickly in case of faults. It depends on the technology, it depends on the, also the voltage level and so on. But let's say 20, 30, 40 milliseconds are the common time for circuit breaker reaction time. And here, the important thing is to be able to detect the deviation in the reaction time. If you you can detect that the reaction time becomes longer and longer, then it's also a sign that something is aging, maybe. It could be the control circuit of the circuit breaker itself, or the active part is in the circuit breaker itself. It could be many things, but a deviation in the reaction time is the sign that something is wrong could happen. And in this case, again, you can see send a maintenance team. And the important thing here is that you don't have to react immediately, but you can plan in advance your maintenance. And in this case, this is a kind of preventive maintenance, because you can react in advance and plan it correctly, avoiding too much stress, and dispatching your maintenance resource properly. These examples are quite simple example, but of course there are many others use cases, partial discharge with more with model behind, and step by step also the use of artificial intelligence to improve this step by step. But just to show that the data collection, or the process of the data that are collected, bring added value for operating the network, for the maintenance, and to make this network more robust and stable, just as some example.
You mentioned the data. You're accumulating more customer data than ever before. How do you feel about your role and the responsibility that you all play in protecting these customers as you're collecting all of this data?
First, this is completely true that the amount of data generated by the systems from the systems increase a lot. And more, we propose to the customers to collect this data, putting them onto the cloud. Because of the added value they can provide, of course. Our responsibility here is to guarantee the customers that the data remains completely in the ownership of the customers. It's not Siemens data, it's data of the customers. Our responsibility is to make the system, cloud application, but also system secure. It's about cybersecurity, it's about the policy, how to handle the data, and so on. And our responsibility is also, I think, to give good advice to the customers, what kind of data are valuable, not collect everything, because it's collecting a lot of data has also some cost. Our responsibility is to select the most convenient data for the application we want to propose, or for the service we want to propose to the customers. But if I try to summarize, it's about the robustness of the data collecting system, it's about cybersecurity, but it's also about the value proposition that we can generate from this data.
I want to just discuss the topic of sustainability and the consumption of raw materials. Siemens is designing its products with sustainability in mind. So how are you all as a company walking the walk, if you will?
In fact, there are, again, different ways, initiatives, actions. Starting with the eco-design of the product, of course, we are improving step by step. The eco-design of the product is also a topic related to the supply chain. We are buying electrical components, we are buying a lot of things to produce our own devices. And this story, this a cross, let's say, cross-company story, because the whole chain should be eco-design. But of course, we have a big role to play here, and our resources, our R&D, is our sustainability teams that are completely committed and dedicated to improve the product. One of the example could be the SF6 band. We have now in the switchgear products without SF6 gas. Also, it is called Blue GIS. Also, SF6 is a gas that is equivalent to a lot of CO2 emission, and this is now in the new US products replaced step by step by what we call clean air, and without any equivalent CO2 emission, and it is a typical example for the much more sustainable products. I give this example for switchgear, but there are many other examples for electronic devices. This is one example. And another one is linked also to innovation that we can provide. In the world of substation control system, we have to connect many equipments, taking measure from the electrical process and sending it to different equipment, IEDs, and so on. And in conventional system, you have quite long hardwired connections. That means copper, raw materials. And with innovative technology like the process bus, and it is an industrial products provided by Siemens since years, you can reduce the amount and the length of the classical hardwire connection. You can also, with other technologies like LPIT, low power instrument transformer, replace conventional CTs with a lot of coppers through LPITs without any coppers, and with a lot of other technical advantages. And these kind of things put together create or makes possible to design a system that is much more sustainable than before. And in addition to the big reduction of raw material consumption, you have also some advantages in terms of electrical power consumption, auxiliary power for this kind of system. Of course, compared to losses on the transmission line, it's a small thing. But if you consider the number of systems deployed in the grid, then if you accumulate all of this, then you can generate a lot of savings also in terms of sustainability. And just to give a last example, that is an important one, I think, through the virtualization of the system, we can avoid a lot of CO2 emission in the engineering phase of the system. A system has to be engineered, has to be tested. It's about pre-FIT, before the FIT with the customers. And for complex system like protection and substation control system, you have to perform a lot of tests, sometimes weeks, on even for bigger system, months of tests. And if you can virtualize your system, at least for this pre-FAT time or for the debugging of the configuration, then you can save a lot of traveling. And we made this experience with the system, and before, at the beginning, we had to perform this pre-FAT test during 6 weeks. And that means traveling to the test platform where the cubicle were, and through the introduction of virtualization, that means digital twins of our protection and substation control system, we were able to do 60 or 70% of the test with a virtualized system. It could be done at home office, so in the home office, it could be done in the normal office, but you don't need then to travel to the test platform, because test platform could be quite far away from your office or from your home. And with this, then you save traveling, CO2 emission. You don't need a car, you don't need to take the plane. And with this kind of innovation, together with what I mentioned before, process bus, LPIT, and so on, SFC, BlueGIS, switchgear without any SF6, step by step, we can create a system that is much more sustainable. And I think it's only the beginning, because more and more through innovation, through redesign, through development, R&D, and so on, then we will put much more other interesting solutions in terms of sustainability, but also in terms of efficiency.
Saving costs, increasing efficiency for customers.
Sustainability.
The sustainability aspect.
Yeah.
I know this is a difficult question, but if you can look into the future of the energy transition, let's say 5-10 years down the road, what trends do you see for automation, electrification, or otherwise?
First, I think that due to the increase of the complexity of the grid, as we discussed before, we need to monitor, measure much more things, values. That means also collecting much more data, being able to put much more intelligence everywhere, but including in the substation, to be able to react fast and properly, correctly in case of events. And we know from the climatic topic, there are much more and more events, floods or storm, whatever. And through that means that the trend towards digitalization will follow and will increase, I think. And the trends in terms of data collection and intelligent processing of the data, it's not only about data collecting, will also increase. And I'm also confident that thanks very interesting innovation, we will be able to improve further the degree of sustainability of our system. And in terms of functionality, thanks to the increase of the processing capability, starting with the processor, but also with the whole system, then we will be able, I think, to face more complex situation, to use better the available capacity of the transmission lines, of the grids, and to combine this technology and to face the challenges what we will have to face. I think we should accelerate because the most challenging is in front of us. And but if we can create a kind of frame of cooperation between stakeholders, customers, technology providers as Siemens, but also the whole constellation of stakeholders that have a role, including governments and the authorities in general, then I think we can reach an interesting step and define a way for much more sustainable futures. Net zero, the gap is huge. It will be challenging, but I think that there are many interesting technologies, but also a good mindset to go in this direction.
On that note, Ronald, thank you very much for these insights.
Thank you.
Thank you all for joining us. And for more, please join us on the Enlit community.